So we already know that trig equations tend to have infinite solutions because of the periodic nature of trig functions. Trig identities are also helpful when working with trig equations because they can simplify the solutions around. So make sure you're always considering the general solution, which are infinite in nature, and solutions that are bounded. In this case, we have a bounded between 0 and 2 pi, and we're looking at this trig equation here. This really doesn't need a trig identity. This is actually the quadratic in form that we've seen before. So if I say y equals sine x, then I get 8y squared plus 6y plus 1 equals 0. And I can factor this thing down into, let's see, it's going to be 4y, 2y, and then they're going to be both plus 1 plus 1. I get 4y plus 2y is 6y, 4y times 2y is 8y squared, 1 times 1 is 1. That looks great. So now we have two different trig equations that we have to work with. We have this one and 2 sine x plus 1 equals 0. And each one of these has to equal 0 over this bounded range. Again, we're only looking for solutions in 0 to 2 pi. So we do not expect there to be infinite solutions in this range. Okay, so for 4 sine x plus 1, the only way this can equal 0 is if this portion equals 0. Subtract 1. And then divide by 4. So we get negative 1/4. And of course, we are looking for also 2 sine x plus 1 equals 0. Same process, subtract 1, divide by 2. We get sine x equals negative 1/2. Okay, looking at these two portions, we have sine x equals negative 1/4 and sine x equals negative 1/2. If we were to look at the unit circle, sine x equaling negative 1/4, negative 1/4 is just about here, and negative 1/2 is just about here. And if I create a line out from there, this is of course the y value equaling to negative 1/4 and negative 1/2. You can see that sine is the, sine x is the y value, is going to be 4 different spots on the unit circle. So we expect there to be 4 solutions. And if we were to look at arcsine for this, like do x equal arcsine negative 1/4, we will only get 2 solutions because arcsine is limited in its range of values that it gives you an answer for. It's limited to the negative pi over 2 to pi over 2. So it would only give us really these 2 solutions. It would give us as a negative angle, but we can just create that into the 0 to 2 pi range, which is not a problem, but it only gives us 2 solutions, and we need to have all 4 to answer this question completely. So to do that, what we can really do is just graph it, and we can see that, or we can look at, of course, this angle is quite easy to find because negative 1/2, this is a special angle. Really, this is the same thing as, this would be negative 1/2 right here. If I create a reference triangle out of that, but really this thing comes from a 30, 60, 90 triangle, and we're at 30 degrees smaller than 360. So 330 degrees is what we're looking for, not negative 30. It has to be within the 0 to 2 pi range. That's the same thing as pi over 6 less, so it's going to be 11 pi over 6. Just they put it in radians. And this is also the same thing. This is pi over 6 above this pi angle. So it'd be, let's see, 6 pi over 6 plus pi over 6 is 7 pi over 6. So we have these 2 solutions. That's going to be this angle here and this angle here. Those are the easy ones because negative 1/2 is one of the standard solutions to sine that we can find by hand. Now this one, of course, is less so. This one is not a nice one to work with. you could look at doing the arc sine. If you're to do that, you're going to see you're going to get x equal to negative 0.25. And that's going to be this first angle here. Let me clean this up a little bit. Let's see, it's going to give you this first angle right here. So this is the radians for that angle. It's the negative. We don't want the negative angle, but that's easy to rectify. Just do 2 pi minus 0.25. It's really 253. I'll go one space further. That gives me 6.030 radians. And then what you can also do is, instead of subtracting that from 2 pi, we can also add it on to pi, because that's the same angle right here. It's hard to see on this small diagram, but it's the same thing as pi plus 0.253. That's going to give me 3.395. So we get two more angles. We get 6.030 and 3.395. So we have 4 angles in total. This is all just trying to find the angles using the unit circle, but you can of course graph this, and we're setting it equal to 0. So we're looking for the x-intercepts of the graph. Here's the graph. It looks kind of strange. We're in this 0 to 2 pi range here. So starting from this spot all the way to 2 pi, you can see it crosses the x-axis 4 times. 3.394, that's what I have here. 7 pi over 6, I have that one right here. 11 pi over 6, that one I also found. And finally, 6.031, which is this angle right here. So I found all 4 that I was looking for. Okay, for this trig equation, this should look like to you 6x, 11x, 6x, 11x. This is a sum or a difference of 2 angles inside of a trig function. I'm not sure which one it is. Let's look at a trig identity. You can, once again, you can always Google this, put it in a search engine, find, just type in trig identities, look up a sheet of paper that has all of them listed there for you. And this looks like, to me, it's got cosine, cosine, sine, sine. That's going to be a cosine double angle, or a cosine sum difference identity. And it looks like it's going to be cosine 6x plus 11x equals negative 0.1. Of course, 6x plus 11x is just 17x. And we're still looking for the solutions between 0 and 2 pi, just like we did for the previous problem. So we're not looking for infinitely many solutions, just those specific solutions. So this one, you can think of this as, let's see, a unit circle. Cosine is the x values. So negative 0.1 is going to be here just about. And there are 2 solutions for just cosine x equaling negative 0.1. So we expect there to be 2 solutions for that. However, the fact that we have 17x in here makes it more likely that we're going to have more solutions. And so a way we can do this is actually look for the general solutions of these 2 points, and then divide out the 17 and look within that range of the k values, which we'll see in a second. Which ones are within this 0 to 2 pi range. So it's going to be 0 to 2 pi. So the general solutions, they're going to be two different ones. We're going to be this one here, this angle, and this angle here. The first one is just going to be quite easy to find, because we can just do the arc cosine for that. So x equaling arc cosine of negative 0.1. That's going to give me 1.671. And that's just about this angle right here. And for this one, all I really need to do is figure out what's the distance. Let me kind of exaggerate a little bit more. All I need to do is figure out what is this angle here, because that's going to be the exact same as this angle here. So if I can figure out that one, which is quite easy, we just take, this is pi over 2, right? And that's 90 degrees straight up. So we take 1.671 minus pi over 2, and that'll give me this small angle. I get 0.100 radians. Okay, that's the same thing as this angle. This full angle here, all the way around, that's 3 pi over 2. And we're going to subtract off this thing from there. So 3 pi over 2 minus 0.100. That's going to give me 4.612. Those are my two angles. X equals, I should say 17x here equals this. But it's not just that, right? It's also both of these things. Because our cosine only is limited between 0 and pi. It never goes above pi, so it will never get to this angle here. So 17x is going to equal 0.100 plus k times 2 pi. Those are all the angles, where k is just an integer. And 17x is going to equal 4.612 plus k times 2 pi. Where again, k is just any integer. And this is important because now we can divide by 17, divide by 17, divide by 17. So now we get two general solutions here. We get 0.100 over 17 plus k times 2 pi over 17. X equals 4.612 over 17 plus k times 2 pi over 17. And when we look at k values, this is a much smaller portion that's being added onto it. And that means there's going to be a lot more solutions to this, right? I could choose k equal to 1, and that's going to be in here. K equal to 2 is going to be in here. K equal to 3 is going to be in here. But there's going to be lots of solutions. There's probably, I would guess there's going to be 17 solutions of them. And so this one really, we should look at a graph because there's just so many. So these are the general solutions. We don't want the general solutions, remember. We want only solutions between 0 and 2 pi. And that is going to be easier to see on the graph. So let's go ahead and graph this. I'm going to move the point, the negative 0.1 over by adding it. That's what I have here. I added 0.1. And we're looking for 0 to 2 pi, right? Well, let's put it in pi increments. And you can see there's lots of solutions. We have this one, this one, this one, this one. I mean, there's so many that it's hard to even see. And so if you count up all of these solutions, there's actually 34 of them. And that's because we had two solutions and each one got divided by 17. So how that ends up working is about, there's going to be 17 different solutions. That tends to be how it works. So it's 34 solutions in total. That's why I didn't bother to find each one. It'd just be too many. But all you have to do really is find all the k values that give you this. So probably between k, I would guess like k negative 3 up to like 14. That's just a guess, but you can just test the values of k and find all the ones that are between that are in the range 0 to 2 pi here. All right, for this one, there's a few trig identities I can use here that's going to help me out. So first off, let's add sine squared x to the other side. It's going to give me 2 tangent x over 2 minus secant squared x equals cosine squared x plus sine squared x. This should look familiar to you. This is the Pythagorean identity, and it just equals 1. And this one is also kind of familiar. It's not quite there, but to me it looks like the double angle formula, which says tangent of 2 theta equals 2 tangent of theta over 1 plus tangent squared theta. It's 1 minus tangent squared theta. And this is almost there, right? It's got 2 tangent x on top. We have secant, but there's actually a Pythagorean identity that can change tangent 2 or secant squared to tangent squared. And that's what we want on bottom. We want tangent squared. So let's look at that. That's tangent squared theta plus 1 equals secant squared theta. And I can just plug this thing into there. We're going to get 2 tangent x over 2 minus tangent squared x plus 1 equals 1. Distribute the negative. You can see that the 2 minus 1 cancel. That's going to give me 2 tangent x over 1 minus tangent squared x equals 1. But this is just tangent squared. So we get tangent 2x equals 1. Okay, once again, we're looking for angles between 0 and 2 pi. Now, because tangent is pi periodic, we expect there to be kind of similar solutions, right? Normally, tangent looks like this, and then for 2 pi, it's gonna go like that, and then I think there's gonna be actually one more. However, this has been adjusted a little bit with 2x, so you could think of this as being horizontally stretched or flattened. In this case, it's gonna be horizontally flattened, so there actually is gonna be more solutions. So we don't have to take arctangent of this thing to find it, because this one's actually quite easy to solve. Tangent equals 1 when you have pi over 4. So 2x will equal pi over 4, and then every pi over 4 equals that. So I can say plus k times pi. It's pi periodic, so every pi is going to be pi over 4 again. So it'll give you 1, where of course k is an element of the integers. And we divide by 2, we're going to get x equal to pi over 8 plus k times pi over 2. Now, this one should only have, I think there's only 4 solutions for this one. So I'm going to actually try and find all 4 of them. I'm looking for the k values. So first off, when k is 0, we have 0 here, we get pi over 8. So pi over 8 is a perfect solution. That's within the 0 to 2 pi range. So that works. Now, when k is -1, we get negative pi over 2. Negative pi over 2 is the same thing as negative 4 pi over 8. Plus pi over 8, it's going to be negative 3 pi over 8. That's a negative angle. That's not in this range. So negative k's don't work. Let's try k equal to 2. 2 will give us just pi. Pi is the same thing as 8 pi over 8. Plus pi over 8, that's going to be 9 pi over 8. That's within this 0 to 2 pi range, so that's perfectly fine. Let's try k equal to 3. We get 3 pi over 2. That's the same thing as 12 pi over 8. Plus pi over 8, it's going to be 13 pi over 8. I think that's going to be the last one, because we have to try k equal to 4. It's going to be 4 pi over 2, or the same thing as 2 pi. 2 pi is the same thing as 16 pi over 8 plus pi over 8. That's already above 2 pi. So just realize this is k equal to 0. This was k equal to 2. And this was k equal to 3. I skipped k equal to 1. When k equal to 1, we get pi over 2. It's going to be 4 pi over 8. 4 pi over 8 plus pi over 8 is going to be 5 pi over 8. So there are 4 solutions total for k 0 through 3, and so that's what we're going to expect in the graph. So graphing this, we're looking for when is this thing equal to 0? I subtracted cosine squared over, and we're going to look for when is this thing equal to 0, or what are the x-intercepts. And here's the graph. You can see I've moved cosine squared over. So the x-intercepts of this are pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. This one is a little too high above 2 pi, so it's only those 4 solutions, and they're the 4 that I had found. So really use graphing utilities to help you solve these things, but also trig identities will help you as well. Give it a try in number 8.